Let's have another look at electrochemical cells. Continue our look at electrochemical cells. Last lesson we looked at a scenario where we were using metal electrodes in solutions that contain their ions. Yeah. So, for example, we would have had something like this. Where if we had in this half cell, what are we going to have? Let's say this is a nickel, and this is copper, and then this would be nickel nitrate, say, and this would be copper nitrate solutions. And we might be told in the question that this is what we have, nickel 2 plus, nickel and Cu2 plus Cu. So that's what we're given in the question. We then go to our electrochemical series and we find these two half equations with the nickel and the copper. And because we know that the stronger oxidizer reacts with the stronger reducer, then that means that we must be reducing the copper ions to copper and oxidizing the nickel to nickel 2 plus. Okay, that must be the way the reaction is going to proceed, which means that the nickel is the anode, which has the negative charge, and the copper is the cathode with the positive charge. Our electrons travel away, they're repelled by the like charge and they're attracted by the opposite charge. And so nickel ions are moving into solution and the copper ions are moving out of solution. We also know that to complete the circuit we need to have a salt bridge, which is, in the context of these beakers, probably a piece of filter paper that's been soaked in a saturated solution of often sodium nitrate or potassium nitrate. And we use them because we can't oxidize or reduce them or precipitate them. And this is where a common mistake is getting which way they travel mixed up. Because we're losing a positive charge here, if you like, we need to replace it. And because we're producing a positive charge here, we need to balance it. And that's the way those ions will move in solution. Now, I did briefly talk to you about what happens if we've got a metal ion changing oxidation state, as in the Fe2 plus Fe3 plus example. But the one I want to, and we remember we needed to use an inert electrode to enable that reaction to take place. Well, what happens if we're reacting gases? So just say, instead of this information that we have in a question, just say we've got Cl2 gas and Cl minus, and let's say H plus nucleus H2 gas. Remember that in this shorthand notation for a half cell, the most oxidized state is mentioned first. So this one has 0 and this is -1, this is +1, this is 0. So that's the order that they need to be in. Now we need to look and find those two half equations on our electrochemical series, and I can see here we've got the chlorine one up the top and we've got the hydrogen one here. So knowing that our stronger oxidizer reacts with our stronger reducer, we're going to have the chlorine being reduced to the chloride ion and the hydrogen being oxidized to H+. So that means I know which way to set up my, I might just move that down a little bit. I know which way to set up my beakers. This is my oxidation reaction. Yeah? So I'm going to need a delivery tube. Over the top of an inert electrode. Okay, so this might be a platinum electrode. And I'm going to deliver hydrogen gas. I'm going to have bubbles down here next to my electrode, and then coming off my electrode will be the hydrogen ion, because that's the oxidation reaction happening there. For my other side, I've got reduction happening. And so I'm going to need a similar arrangement on this side. Oops. Where this again is a platinum electrode. I'm going to be delivering chlorine gas. So there's bubbles down here, and then coming off is the chloride ion. And the opposite would be the arrangement if I happened to be producing a gas. Then I would have a collection tube so that I would be able to gather that gas up that's coming off the electrode. So this is still the anode with a negative charge. And this platinum electrode here is the cathode. Positive charge. And just making sure that we've got them around the right ways. So we've got H2 going to 2H plus 2E minus is obviously oxidation. And reduction here, Cl2 gas plus 2E minus goes to 2Cl minus. Okay, so that confirms that I've got my half cells around the right way and I've got the reaction around the right way. Does that make sense? Okay, so it doesn't have to just be the metal electrodes in the solution of their metal ions. We can do it for other substances as well.
Sorry, why is the arrow going the other way for the chlorine ions?
The chloride ion
Yes.
is coming off the electrode because that's our product.
Why is it coming off there, but I know like an example of how it's going on to it?
Because this was a cation here, the copper ion it has two positive and it is gaining 2 electrons to become copper solid. The chlorine gas is gaining 2 electrons to become the chloride ion. So the chloride ion is then can't really stay stuck on the electrode there. It's going to come off into solution. And it also makes sense in the context of our balancing of our ions here that the positive ion is still coming down to balance our newly formed negative ion. It's a matter that metals here, the reduction of the metal would stay on the surface of the electrode, whereas the ion isn't going to stay on there. The ion will move, it'll be more a function of concentration then. that eventually they'll diffuse out into the solution. Alright, so this is another application of an inert electrode is with gases, just like we saw with the change in oxidation number for our metal ions such as Fe2+, Fe3+. But it could be tin 2+, tin 4+ as well. That would be another common combination that you'd see. Any other questions? Okay.